5, 4, 3, 2, 1. Okay, let's go. Right, so we're working on what to do with assignment 1. We have a plan and we'll let you know soon. Assignment 1 is MIPS assembly. So, if you want to know how to do it, if you want to know how to do assignment 1, pay attention today. There'll be labs on MIPS assembler for the next couple of weeks as well. Alright, so today we shift, it's a little bit of shift in focus. Last week we were talking about data representation, which is how you interpret the bits inside a word. And now we move on to MIPS assembly code, which basically deals with how you shuffle words around and how you modify the values contained in those words. So shuffling words from memory into the CPU, making changes to them and then pushing them back out again. So today we'll talk about general CPU organisation. So I'm going to say things, I'll say things at a general level and then I'll be a bit more specific and talk about how these things are implemented in terms of MIPS. Assembly language and MIPS in this context is useful to know because it gives you, I hope, some insight into how the C language works when it actually runs. So when you compile your program and execute it, a lot of people, I get the feeling, aren't particularly clear on pointers, aren't particularly clear on pointers to structures, aren't clear on what it means to pass the address or a pointer to a function and then see and getting stuff back out of that. So hopefully all this stuff will make all of those kinds of ideas quite clear because you have to deal with them in excruciating detail when you're manipulating things with assembly language and always do that. Right, so here's another nerd. Who is he? What did he invent? I will put money on absolutely nobody knowing who this guy is, because I certainly didn't. So here's a clue. Here's what he invented. Another one of those giant machines with refrigerator ladies operating it, doing all the programming. But his name is Tommy Flowers. And what did he do? He designed and built a computer called Colossus, which was the world's first programmable electronic computer. And he was working at Bletchley Park with Alan Turing, cracking German codes in World War II. So he built this machine and decided, hey, this seems like a good idea. Electronic, programmable, electronics reasonably fast. We can do lots of interesting things with a programmable electronic computer. Unfortunately, he failed to convince anyone that electronics was a good way to go and that programmable machines were at all useful. It's a bit strange looking back in hindsight that people might think that, but they did. So in the end he gave up and he went back to working on telephone exchanges, which is a bit sad. I seem to be picking a lot of losers for these famous system nerds, but it's interesting to see the people who tried stuff who actually made some breakthroughs but then couldn't follow through with them. Well, not necessarily their own fault. Alright, so this diagram should look familiar. So a typical computer system has a CPU, central processing unit, which talks along a system bus to all these different kinds of devices. The most important device, which is the memory at this stage, because when we're fiddling with MIPS assembler, basically what we're doing, we're talking about data going backwards and forwards from there to there. There is a little bit of trickery in MIPS to get the processor to talk to I/O devices as well, but that's pretty minimal, the way we'll be dealing with MIPS. So basically it's talking about data going backwards and forwards between those two things. Alright, so we've seen that architecture before. Now I wanted to have a look inside the CPU. So if we open it up and look in the box, what do we find? Very small box. A set of registers. So a register is basically 32 bits of information that can be treated as a single entity. So there's a bunch of registers that are used for holding data values, a bunch of registers that are used for controlling how the machine works when it's executing programs, and there's typically an arithmetic logic unit as well, into which you can feed the values of two words, perform some operation on them, get a result out, and store it into another word, into one of the other registers. Access to random access memory, so the CPU can push stuff to the memory, it can fetch stuff from the memory, and that's the extent of its interaction with the memory. Push stuff out, fetch stuff in. And typically what you find in a CPU, or what a CPU implements, is a bunch of very simple operations. So you can push data backwards and forwards, as I was saying. You can push data through the ALU, and you can make tests. These first two things by themselves would be okay, but they wouldn't give you enough to write programs, to write general programs. So critically is this stuff here, which basically gives you iteration and conditional execution. So you can check whether, for example, two registers contain the same values. So you're doing an equality test. You can check whether one's greater than the other, and so on. And when you discover what the condition is, you can transfer control of execution to a different instruction in the program. And if you discover they're not equivalent, you go somewhere else and execute the program. We'll see a lot of how that all works together. So that's a very general view of what you find in a typical CPU. Different kinds of processors, if we're talking MIPS or Intel or whatever, will differ in the number of data registers, the particular control registers they have, maybe what operations the ALU supports, maybe whether they have a floating point operational unit as well, how much RAM you've got, of course, but that's not really part of the CPU anyway. And certainly they'll differ on the set of instructions. Now, the black textbook that I've been recommending looks at the Intel CPUs, and that's a particular kind of processor that has a large collection of different operations that it can do. So those kind of processors are called complex instruction set computers, okay, CISC. MIPS, on the other hand, has a relatively small number of operations that it knows how to do. And those kind of computers are called RISC computers, reduced instruction set computers. Now, there's a lot of engineering trade-offs in which is better. RISC has the advantage that it's very easy to build the hardware. CISC, you've got to build a lot more hardware. On the other hand, if you're writing programs to work on a RISC machine, you generally have to write more instructions than you'd have to write in a CISC machine. But each instruction on a RISC executes faster. So you've got all these trade-offs going on, and which is better? It depends on the program you're trying to execute generally. Right, so here's the internal diagram of the CPU. So here's our data registers, here's our control registers. What do they actually do? We'll see in a minute, but always there's going to be one important control register which tells you what is the address of the next instruction to execute. Everything starts life in the memory and eventually gets dragged into the CPU, typically into the data registers, or maybe it gets dragged into the control registers if it's an instruction that we're actually executing or an operation to be done. The ALU sits there and we shunt data from the data registers into the ALU, perform various transformations of it, and then typically stick it back in the data registers. From there, you can push it back to the main memory. So there's generally two data shunting operations. There's a load operation which will pull data in from the main memory into the registers, and there's a store operation that will take data that's currently held in a register and push it out to some location in memory that you specify as part of the store operation. So how do these CPUs work and what does an instruction look like? Well, it depends. It depends on the architecture, it depends on the instruction itself. So, for example, we might have an instruction where the first 8 bits are used to represent the operator, the operation that you're trying to perform, which could be multiply, could be add, could be make a test, it could be jump to a particular location in the program. And then we typically have, and here this would be very typical for an operation like add or multiply or subtract, where we've got our add operator, we've got a register which tells us where one of the operands lives, we've got another, the identity of another register which is where the other operand lives. These two values are taken, shunted to the ALU, and then we store the result in a third register, which is the destination register. So in C, you'd write that, you know, like x equals y plus z. Here you're kind of writing add y, z, x. Okay, so add those two values that are stored somewhere, and then store the resultant value into somewhere else. So that's one kind of format, and a typical machine will have, you know, lots of different kinds of instruction. Well, I shouldn't say lots, it'll have a couple of different kinds of instruction formats. So here's one possibility, here's another one. This would be typical of a load or a store operation. So the operator, once again 8 bits, will say load. Destination is where do we want to load into, so that would typically be a register. And where do we want to load from in the memory? This would be a memory address. Now one thing that you can see straight away by looking at these things, how many different operations could this machine, this mythical or imaginary machine do? Given that we've got 8 bits, that's 256 different operation codes. So one of them could be add, one of them could be multiply, subtract, divide, load, store, test, blah, blah, blah. So up to 256 different operations. If these operands here are registers, then how many different registers could this machine address? Once again, 8 bits. So this machine, this imaginary machine, could have 256 different registers. Most machines will have a lot fewer than that, so you wouldn't necessarily need 8 bits to represent the two operand addresses. So often the word will be, you know, I've partitioned it up nicely, 8888, but typically you'd have a lot less than 256 operation codes. So maybe you've got 64 different operation codes, certainly in a RISC machine. So say 64, so therefore for those you only need 6 bits. And if you've only got 16 registers, then to address 16 registers you only need 4 bits. Okay? So in fact, potentially we could stick the 2 operands into 2 4-bit chunks. We could have 6 bits used to represent the instruction and so on. And okay, that looks a bit silly here because we probably end up wasting bits. So if we got 4 bits for a register, 4 bits for a register, 4 bits for a register, that's only 12 bits. And if the operation code is only 6 bits, so 6 and 12 is 18, so you know, we've got an annoying number of bits, and we've got 14 bits that we're probably not going to use. And that would not be atypical either, that there would be some bits of the instruction that weren't actually used for any purpose. Down here, so we've got the operation, still 8 bits, where the value is going to be placed or where it's coming from. So that could be 4 bits if we're dealing with 16 registers. And that would leave us, so if we had 6 and 4, that's 10. that would leave us 24 bits of addressing power. So if we've got only 16 bits of addressing, then we can deal with 2 to the 16 different memory addresses, 0 up to 2 to the 16 minus 1. Right, so what kind of operations does a typical CPU have? Once again, these aren't from any real machine, they're just giving you the general flavour. So there'd typically be a load operation which takes a value that's currently stored in a memory address and makes a copy of that value into one of the registers. So that would have 2 parameters, the name of the register to store into and the memory address to get the value from. Then another typical kind of operation is something that would load a constant value into a register. So the actual value that's being loaded would be contained in the instruction. Whereas in this first case, what's contained in the instruction is a memory address. We go to that memory address, we get the value from that memory address, and that's the value that goes into the register. Here we're getting the value to be put into the register directly from the instruction itself. Store instruction takes a value currently contained in a register and copies it into a particular location in memory. A jump instruction would change the value of the PC register, the program counter, and transfer control of the program to somewhere else. So you're currently executing you do a jump instruction and you go somewhere totally different and then start executing again. We'll see how all this fits together when we start writing programs in MIPS. And pretty much every architecture is going to have some kind of instruction. It won't necessarily be called jump if, but something for taking a status value or a Boolean value that's currently stored in the register, and then if that value is true, it jumps to a different part of the memory. If the value is false, it just goes on to the next instruction. So that's how you can implement if statements. And then we've got typical kind of instructions. We'd have add, subtract, multiply, divide, which would take 2 registers, combine them and store the result somewhere else. We'll take the values in 2 registers. So we've also always got to be careful to distinguish the address or the location of the value that we're talking about and the value itself. So given 2 registers, take the contents of those 2 registers, combine them and store the result in another register. Similarly, you typically have a number of bitwise operations. A unary bitwise operation that will just invert the value, the bits stored in a particular register, and store the result in a different register, which potentially could be the same if you want. So if you just want to modify the values in a particular register, you can do that. Typically there'll be a shift operation, shift left, shift right. So all the kind of operations that we've seen in C recently would exist. And finally, there'll generally be some kind of special operation which allows you to access special, I want to say operations again, so I will. So a special kind of instruction that allows you to execute special operations which require privileges above what a normal executing program might have. And so system calls, and in the case of MIPS, we've got system calls to read values in, system calls to write values out, and so on and so on. And we'll have a look at a lot of them in a minute. So when you're dealing with MIPS, you don't have something like the standard I/O library. You're dealing with things that are very low level, and the only way that you can do input and output is by using a system call. So when a program's executing, basically it behaves something like this. So it sits there and runs forever while it's executing. It uses the PC register, goes to the memory, grabs the value at that memory location and stores that in its instruction register. and then increments the program counter so it moves to the next instruction in the memory. If the instruction happens to be a stop instruction, then we break out of this execute forever loop. Otherwise, we execute the instruction that we just read in, that we stored in the instruction register. So the program counter is an extremely important register. It tells you where is the next instruction in the program to be executed. And as I've already mentioned, the program counter can be modified by various kinds of operations. If the operation doesn't modify the program counter, then we can see that we've already incremented it here, so it would just go on to the next instruction. So the kind of the default behavior, execute this instruction, then execute this instruction, then execute this instruction, and so on. But a jump instruction, as I said, breaks that sequence and you go off somewhere else and start executing over there. Right, so we already had a little bit of a look at how instructions might be represented. So here's some slightly more realistic examples. So we've got an add instruction, 2 registers, and a 3rd register, which is the destination. Load instruction, load into a particular register, and store the result in some address. Now, of course, inside the machine, these aren't going to be represented as R1. They're going to appear simply as an 8-bit quantity, and the machine, the CPU, has to interpret that as meaning register 1, because it happens to appear in the second 8 bits of an instruction. So it looks at the first 8 bits and says, okay, that represents the add instruction. Good. Where am I going to get my values from that I want to add? I'll look at the second 8 bits. That'll give me a number which represents one of the registers. Then I'll look at the third one of 8 bits, gives me another register, and then I grab the values stored in those registers, run them through the ALU, add them together, and I've already got a 3rd register address here, and I can store the result there. Similarly, a load into a register from a particular location in memory. So if you wanted to look at those instructions, actually see them, they're basically going to be 32-bit bit strings. So for example, that first instruction, something similar to the first instruction that we had, this might be the code, the 8-bit code for the add operation. This might be the 8-bit code to represent register 4. You can see that those 8 bits give you the number 4. This might be the 8-bit code for register 16, and this could be the 8-bit code for register number 1. Now, if I didn't have these things written here, these comments, and I just asked you, what instruction is that? You're just looking at a bit string and you wouldn't have a clue what it was doing unless you're extremely nerdy and happen to know the bit patterns for all the instructions in that particular architecture. So looking at instructions like this, in theory, and this is what people like Tommy Flowers had to do, if they wanted to program their computers, they'd have to type in a bunch of bits like that, typically on paper tape or something like that, feed them into the machine, and then the machine would run through that execution cycle that I showed you a couple of slides ago and execute the appropriate instructions. So the way you put your program in was in that format there. That's clearly not useful for us to do programming, although if I really wanted to torture you, that would be an interesting thing to do. So a long time ago they invented the idea of assembly languages, which are really just a symbolic way of writing those instructions that we had on the previous slide. So here's an example. These are actually MIPS instructions. So you can write instructions. Now the instructions themselves are just that part. This is a data definition, okay? So a couple of things to notice. You can write the instruction, so load immediate is the instruction there, load word, load immediate, and here we've got an add instruction. So at least you're not looking at an 8-bit bit string to try and work out what the operation is, you're looking at something symbolic Similarly, you can refer to the registers using moderately symbolic names, so $T1 is a register, 0 is just a constant value. So what this instruction is actually doing, it's the equivalent of what I earlier on called load C, load a constant. So often that's called immediate. So load the value 0 into the register whose name is $T1. This second instruction, load word, is loading a value into the register $T2, but it's getting that value from the memory and it's using a particular addressing mode to get that value. So it's taking a name, so you can give names to memory addresses, so you don't have to remember. When I defined the object array here, the assembler is going to put it at a particular location in memory. I don't want to remember, I don't want to have to know what that location is and write 0 hex 1000 or whatever. I want to write the name because that's how I know that object. So I can write the name and then in parentheses put the name of a register, and what this instruction is going to do, it's going to work out what that address is, so it does all the hard work of working out that array happens to be located at address 2000. It then takes the value in this register, adds them together, and computes the final address that it's going to load stuff from. So T1 happens to contain 0 at this point, so this load word is going to take the first word from the object array. So in some senses, it's kind of like doing array indexing in C. So it's going to load the value 5, which happens to be the first thing stored in the object, in the part of the memory which is associated with the name array. We then load the value, the constant value 4 into the register T1, and then into register T3 we load the word which comes from this location. Now you can see that we've just modified T1, so it's now 4 beyond where it used to be. So that actually, because of the way the array is defined, corresponds to that value there. So each of those numbers that I've written occupies 4 bytes. So putting in an offset of 0 here says go to the location called array, don't go any further than that, go off beyond that by 0 bytes and load in the value that's stored there. So that's the first thing that happened. Then this instruction here, because I put 4 into T1, says go to the location in memory whose name happens to be array, then add 4 bytes onto that, giving me a new address, and then load the value from that address into the register T3. So that has to be that value there. And then I add them together, so I add T2 to T3, and I store the result in T0. One thing to notice about this is that MIPS actually puts the destination register first. All the examples, the imaginary examples I showed you earlier, I put the destination register last, but MIPS happens to do it that way. In some sense, it looks more like an assignment statement if you do that. So it's kind of $T0 equals $T2 plus $T3 is a way that you can read that. So, important thing is that you can write all this stuff. You're basically still just writing machine instructions like these ones, but you don't have to know what the binary looks like. You can write them in slightly more symbolic form, but each line of that represents a single machine instruction. Alright, so MIPS. So MIPS, one reason for looking at MIPS is that it's reasonably well known and it's also quite simple. So we don't want to chuck some complicated thing like an 80 Intel blah 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 whatever at you. So we'll deal with a simple architecture which happens to have been used in a few older type systems. So we're not actually going to play with a MIPS CPU. It's not going to be something you can hold in your hand and say, hey, here's a MIPS CPU. We're actually going to use a simulator. So a piece of software that reads in stuff like this and effectively execute it like a MIPS CPU would. Now, there's three ways that we're going to fiddle with MIPS code. The basic way is a thing called SPIM. That's a command line command that you can feed in a file which contains assembly code, and it will execute that code for you. The other two, Qt-SPIM and XSPIM, are actually GUI front ends, in which you can monitor in excruciating detail what the machine is doing while it's executing the code. And typically these things will show you all of the registers, they'll show you the instructions. You can say execute the next instruction, and if it's doing an add, you can see that one of the registers changes. And execute the next instruction, you can see that another register has changed. And of course, every time you do execute the next instruction, you're going to see that the program counter changes. Now, just let me see if I can actually, this display here doesn't go, oh that's right, because I access it through here. Where's it gone? Here we are. And it kind of fits. So here is Qt-SPIM. So you can see it's giving me a list of all the registers down the side. You can't see them all because there's 32 of them. It's telling me that the program counter is currently 0. All of the registers except for A2 contain 0. And what it's got here is some system code. And if we look more down here somewhere, we should eventually see, where's it gone? No, we look up here, that's right. So here we see something that calls the main function. Right, we'll talk about what JAL actually means, apart from Japan Airlines, later on. And you can see down the bottom here we've got a syscall as well. What this syscall is doing, it's actually stopping the program. So the program will start executing here, execute those instructions, and then stop. So here's a whole bunch of other instructions which are system related. So if you actually want to run a program, I've got a program that prints hello MIPS. That's not what I wanted. That's also not what I wanted. You can tell I haven't used Qt-SPIM for a while. Let's try that. Haha. Alright, so let me see. Take me out to find it. Silly, I could do a search, couldn't I? Alright, let's try that one. I assume, did that get loaded? No, it didn't. Why not? Haha. Alright, so you can see that this part of the code has changed. We've still got the same bunch of stuff up here that we had. So that's the little chunk of code that actually executes the main program. So when we say C programs start with main executing, there's actually a little bit of code that executes first that calls the main program. Right, and what we've got loaded in here is code that asks me for my name and then says hello to my name. So if I wanted to, I could execute this by saying run, and it's asking me for something, so I can type in John, hit enter, and then it says hello John. Wow, isn't that exciting? But one thing you can see, a lot of the registers have ended up being changed by the execution of that code. So you can see in incredible detail what's happening when you execute your program. Anyway, I'll stop playing around with that. Let's get back to the slides. SPIM is a similar kind of thing. Which is better? I don't know. Some people prefer SPIM, some people prefer QT-SPIM. One important thing about QT-SPIM is that you can download it to run on your laptop. So there's binaries for Linux, Windows and macOS. So whatever machine you've got, you can run QT-SPIM on. SPIM is a little bit tricky. You need a machine that's running an X server, and if you happen to have one of them, that's fine. SPIM, last time I checked, didn't work on VLab, which is slightly annoying, but I'm pretty sure QT-SPIM does. But in any case, so SPIM would be the typical thing that you could use to see if your program's working. Since I'm looking at this, try that. Alright, so that program ran this assembly program called hello1.s, printed out a bit of annoying rubbish, but we just ignore that. And then what the code was actually doing was printing out that message there. Okay, so SPIM takes in an assembly language file, executes it, and then stops. So it's not really like GCC, where GCC has the notion that you do a compilation and then you do an execution on something that GCC produced. Here we're reading in the MIPS assembler and we're directly executing it. So there's no compilation step involved. One other nasty thing which I'll try and fix before we get too much further into the term, I have a feeling the default version of SPIM that's installed runs a different version of the virtual machine than QT-SPIM does. So you can write programs that work on QT-SPIM that if you bring them in here and try to run them, they won't work. It's really trivial kinds of things like the way that you write special characters. So I have a funny feeling \n doesn't work on the built-in SPIM, but it works on QT-SPIM. So we'll try and sort that out. If you want to have a look at the code for SPIM itself, SPIM is written in C, and you can have a look at a large chunk of C code in that directory there. Or if you want to download the source code, you can get it from there as well. Oh, you can also get binaries. Alright, so that's how you use MIPS here. So what does the MIPS architecture actually look like? We kind of saw from that QT-SPIM, we saw that it's got 32 registers. It actually has more than that. It's got 32-bit unsigned int registers, which can be interpreted as signed ints if you want. And it's also got 16 registers, which are 64 bits long. They actually come in pairs, and you can use them for manipulating doubles effectively. It's got a program counter register, and it's also got a couple of special registers, and every architecture will be different and it'll have different special registers for different purposes. But these two registers here are actually used when you're doing operations like multiply, where when you multiply two 32-bit numbers, you might get a result that's larger than 32 bits. And if you do, the result will end up in these two registers here. So each of those high and low registers is 32 bits. So the low 32 bits from the result of your multiplication will end up in the low register, and the leftmost 32 bits will end up in the high register. If you want to talk about it, so most of the time we'll be dealing with these registers, the 32-bit registers. So if you want to, you can talk about them as $0, $1, $2, $3. That's fine, but it's less symbolic than it might be. But registers, some registers have special use, and some registers you want to give them symbolic names so you know what the intention of the use is. I'll talk about that on the next slide. But anyway, some special use registers, $0, you might be surprised, always has the value 0 and you can't change it. Why do we do that, do you suppose? Because 0 is a value that we frequently use in our calculations. So if we're trying to add up a list of numbers, we start with the value 0. If we're starting to iterate through an array, we start with the index value of 0. So having a register that always contains the value 0 turns out to be quite useful. So that's what they've done. So they've dedicated one of those registers to always holding the value 0. 3 more of the registers get used by the system, and they get used for particular purposes like holding the status of a comparison and things like that.
Dr. Shepard.
Yeah.
What does MIPS stands for?
Ooh. That's a good question. What does it stand for? What does it stand for? Don't know. Off the top of my head, I've always just called it MIPS. We can look it up on Google if you want.
I've got it. Microprocessor.
Yeah.
Interlocked pipeline stages.
Ooh. And that information is not at all useful for this course, which is probably why I never bothered to remember it. All that stuff means something, and especially the pipelining stuff is important, but for our purposes it doesn't matter, it's a thing called MIPS. Alright, so register 0, you can also refer to it as the word 0, apparently without a dollar. $1 is one of the special registers, so it's used by the assembler to do stuff when you're executing instructions, as we'll see in a moment. Some symbolic instructions that you write in MIPS assembler actually turn into multiple instructions at the machine code level. So you can almost think of it as there being a very lightweight compilation step involved here. So you write a certain kind of instruction, it turns into a couple of other instructions. Now some of the other registers do have particular uses. So $V0 and $V1 are two registers that are used to return 32-bit values from functions. So unlike C, MIPS functions that you write in MIPS can actually return 2 values. If you want to return just 1 value, then the convention is that you'd return it in $V0. How do we achieve this? We'll show you later. How do you pass arguments into functions? There's 4 registers that are used by convention for doing that. You might say, what if I've got a function that's got 5 arguments? Then I'm stuffed, aren't I? No, you're not, because you can always put the arguments, any excess arguments, on the stack, as we'll see later. But I think if you go through and look at all the functions you've ever written in 1511, 1911, whatever, most of them didn't have 4 arguments anyway. So these registers would be enough. The other thing you might ask, hey, what happens if I'm trying to pass an argument that's not 32 bits long, that's bigger than 32 bits? Once again, you can stick it on the stack, right? So you can stick arbitrarily large data structures on the stack. But if you've got a typical thing like passing an int, passing a char, whatever, you can stick it into one of these arguments, one of these argument registers. Alright, then certain registers have conventional usages. Now, the fact that they're convention means you don't have to follow the convention. But if you don't, and if you don't follow the convention, the process is not going to notice and it's not going to trigger some kind of runtime error. But The reason for the conventions is that if you're putting your program, your MIPS code, in with other MIPS code, the other MIPS code is likely to make assumptions about these conventions. So, these registers $T0 to $T7, which happen to be registers 8 to 15, are what's known as temporary registers. So you use them when you're manipulating values that only have a very short lifetime. So if you're trying to compute the result of an expression, and you need a complex expression, and you need to store one part of the result before you incorporate it with other parts of the result. One thing you may have noticed is that all of the operators in MIPS, apart from the ones that are unary, are binary. So they can only take two arguments. So what happens if you've got some complex expression, x plus y multiplied by y plus z? Okay. So you'll have to compute x plus y, store it somewhere, then compute y plus z, store it somewhere else, and then multiply those two things together to get the final result. So the typical place you'd store those intermediate results is in these temporary registers. Now, one thing about these temp registers is when you're making function calls, which happen to be called subroutines in the MIPS context, when you're making function calls, you make certain assumptions about what things are going to maintain their values after the function has finished executing, and make certain assumptions about things that may not retain their values. So if you think about what happens in C, if you've got local variables in a function, if that function calls another function, when the other function returns, these variables are going to have the same values that they had when you made the call to the second function. You don't expect this function here to change the values of this function's local variables. If you happen to pass the address of one of these, yes, it could, but generally you don't expect them to change. So there are some registers that are going to be dedicated for that purpose. You put values in them, you make a function call. When that function finishes, all of these registers still have the same values in. So these T registers are the opposite to that. So you can put values in, make a function call, and when that function returns, you have no idea what's happened to the values in the T registers. Maybe they've changed, maybe they haven't. So you shouldn't assume anything. So functions are allowed to scribble all over the T registers because the calling function doesn't assume that they're going to be their values are going to be retained. Whereas these S registers are exactly the opposite. So if a function puts values in the S registers, then it calls another function. When the second function returns, the values in the S registers had better not be changed. So they've got to act like C local variables. How that happens, if the called function wants to make changes to the S registers, then it will have to save their values and restore them before it returns. So you start to see that there's a lot of work that goes on when you make a function call, and we'll see that a lot more over the next couple of weeks. And then there's a couple more temporary registers. Why they didn't put them with the first batch, I don't know, but that's the way the architecture is implemented. So functions can scribble all over these two registers as well. These two registers here are used by the operating system, whereas MIPS doesn't actually have an operating, or SPIM, the version of the MIPS simulator that we're using, doesn't have an operating system, but in theory you shouldn't assume that these registers are going to hold a particular value. As I said, all of these things are conventions. So if you want to, you can stick a value in $K0, but in 2 instructions time, if you make no other changes to $K0, there's no guarantee that it's got the value that you put in before. Alright? So the T registers will persist within a small block of code where there are no function calls, S registers will persist even if there are function calls, but these you've got no idea what's happening. Alright, so SP, the stack pointer, is a very important register, and FP, they're the things that implement the function call stack. So when you call a function in MIPS, it has to create a little environment on the stack for itself, and now rather than C doing all the work for you, you have to do it explicitly. So you have to make a stack frame. And the stack frame is bounded by the stack pointer and the frame pointer. Other important thing that happens when you make a function call, the way you make a function call, we saw before, there's a command called JAL, or an operation called JAL, which stands for jump and link. And the link is the fact that it sets up the return address in a particular register, $RA. If you scribble on that register during your function, then you've kind of lost where you're supposed to go back to. So that would be a programming error to mess that up during the call to a function. So if we go back, let's see, to here. Alright, so we fetch a jump and link instruction from the memory. We increment the program counter so we know the next instruction to be executed. Actually executing the jump and link instruction is going to store the new value of the program counter in the $RA register. Right? So when we go and we start executing the function over here, we know where to go back to because it's stored in the $RA register when we make the jump and link, or we execute the jump and link instruction. So that's very important for executing, for implementing function calls. Where are we? Alright, so SP, FP and RA are very important for that. Global pointer, haven't actually used, I don't think, ever. So I don't know what it does. I'm not going to talk rubbish. Possibly, I'll speculate what it might be. It might be a pointer to the highest part of the data region of memory that is currently being used, but don't trust me on that. Go and have a look it up in the documentation, which you have a lot of documentation, by the way. Something that I just alluded to there, and I don't know if I have a slide on it. No. No, unfortunately I don't. So remember that we talked about how C treats the memory. We've got the code in one section of the memory, then we've got global data and string constants, then we've got the heap, and then we've got the stack. MIPS certainly has the code in one area, and then has the global data in a separate area, but it doesn't have a heap. But it does have a stack at the top end of memory like C. So there's certain similarities, but it's not exactly the same setup as we have with C. Right, the floating point registers are used conventionally like this, but we hardly ever use them, so I'm not going to say any more about them. We hardly use them in this course. Alright, so what does MIPS assembler look like? I'll tell you in a minute, because it's time for a break.